Everybody to this last session of this conference. Our first speaker today is Pavel Nikitin, who will speak on rigidity of determinantal and Pfaffian processes.
I'm really glad to be here. How some of you know, it was just the last days when I was able to come after all, and I'm really happy that I'm here, that there are a lot of perfect talks, a really nice conference. Thanks a lot. So, it will be on rigidity for determinantal and Pfaffian processes, and the main result is we should almost turn the order of words. So if I take Pfaffian sine and Bessel processes, then they are rigid. And my plan is now to explain all the words in the definition and in the theorem. To begin with, I want to say you what do I mean by process. You've heard it already, so it will be point processes, and I will be interested only in point processes on R. So I think about the...
Could you write bigger, please?
Even bigger?
Yeah.
Okay. Let me do it. So I'm speaking about the configurations on R, that is the sequences of points without the accumulation, without the finite accumulation points. And if I want to speak about the sigma algebra, it will be important for me. Then I just consider all the counting of points inside the bounded Borel sets, Borel sets, and I say that all these maps are measurable. Thus I have my sigma algebra. And what is the question about the rigidity? I take a configuration. I fix some set C. I fix my configuration outside. The question is, what can I say about the points inside? Sometimes I can say nothing. Take the Poisson point process. But sometimes it happens that there is one particular variable that is fixed, and it is the number of points inside my set. To be more exact, let me now consider a smaller sigma algebra, a subset of these maps where B is inside C. C was here. So it's just sigma algebra sitting outside. And now here is my main definition. I have a point process. Let me say and I say it is rigid if for any bounded Borel A, I consider my map number of points inside A, and it is F R minus A measurable. just the same definition in more explicit words. Now, sometimes it's important to say that it's a number-rigid process because now there is also a notion of linear rigidity.
So that's why you write so small that no one can see.
Okay, yes. But yes, it will be not important in this particular talk. So this is my definition. And there are several ways now to prove that the process is rigid. And I want to state you the definition is due to Ricerca. Gosh. I want to state you when this is true, and I need one more standard definition. Let f be from R to itself, say with compact support. And I consider the so-called counting functional depending on x, where x is one of the configurations. And I just take the points from my configuration and I sum up my function. Because of the compact support and of my definition of the configurations, here the sum is finite. I can define it for more general, but let's do it like this. Now the proposition. If for any, say, A, bounded and any epsilon greater than 0, I can construct f epsilon such that on A it is identically 1, and the variance of my functional SF epsilon is less than epsilon. It is sufficient. Let me say that I have a process. Then it's the variance with respect to my process, and then the process is rigid. How should I? No, it doesn't look like this. Let me write a couple of words why we believe it is true. I look at the definition of my f epsilon and I can find a sequence f. And such that if I consider the corresponding functionals as f n by Barrel-Cantelli, I just have that the difference between my functional and the corresponding expected value tends to 0. So think about it as something really close to constants. Now I consider my functional only on A, and on A it's identically 1. So I just count once. This is equal to the number of points of A. Let me put my configuration here one more time. And now I have the second part, which is SF n restricted to R minus A. And you can believe me that it is in F R minus A. Well, it's not the proof, but you can feel that it should be true. So now we have a criteria. Okay, a sufficient condition.
Due to Gaussian pairs.
Due to Gaussian pairs, yes. Ricerca, Koch, and evil pairs. Thank you, Sasha. And we see that if we want to use this particular proposition, the main thing we're interested in is the variance. Thus I need some nice formula for the variance, and I want to briefly remind you who are the correlation functions. We had a general definition by Andrei, but I will need only the first two. For the first, I have my functional. I consider the expectation. If I can write it in the following way, think of this equality as the potential definition of my density ρ1. Then ρ1 is a first correlation function. Now, if I can do the same thing for g of xy, I have two variables here, and I consider the corresponding expectation of the counting functional for g, it will be the integral over r square of g xy dx dy. Think of it as the definition of the second correlation function. Now I want to write what is the variance. And just by definition, it's the expectation of the product minus of the square minus the square of the expectation. I want to write it in the following way. It will be So you see that here we have just the definition of the first correlation function, and I get yes, this term, and here I have inside the square of the product. If 2 points are different, I get this term. And if the 2 points are the same, that it's again the first correlation function. I get this term. Think about it for a second and you will believe me. Now, what I see here, the second correlation function minus the product of the first ones, it's so-called second truncated correlation function. I will denote it in this way. And now I want to add a subtract one more term. It will be dy dx. So if I combine this and this, I definitely get and if I combine this and this term, once again think of it for a second, and you will get f of x minus f of y squared times the second truncated correlation function. So maybe it's better if I do like this. So it's not that obvious why do I want to pass from this line to this one, but you will see in a second that it will be really important for me. Because if I have a point process that comes, say, from statistical mechanics, for example, the orthogonal ensemble is more or less okay. Then I have the following nice, then I expect the following nice property. Namely, if you look here, what I want is that if I integrate the second truncated correlation function, I want to get minus rho 1 of x. Let me denote it by star. It's called sometimes perfect screening. I can't explain you the details, but it shows that for our statistical mechanical system, there is no external force usually. At least this is how Peter Forrester explains how this appears. And we'll see that in some examples, this property does hold. Now let me come. I will take P, a determinantal point process. Up. That is, I have a kernel K, X, Y, and all my correlation functions, rho n of x1, so on, xn, are just the determinants of the n by n matrix. And the entry of the matrix is just the value of my kernel on xi, xj.
Masha, excuse me.
Yes?
I'm confused. Shouldn't it be a plus before 1/2 at this point? So that the variance be positive.
We will see it in a moment for the determinantal point process.
Okay.
And if I have a determinantal kernel that comes from the orthogonal ensemble, it's usual thing that actually this kernel I will by the same letter denote the kernel and the corresponding process. Then it will be just an orthogonal projection. Orthogonal. What is important for us, it will be orthogonal projection on the finite step, and it will be still an orthogonal projection after the limit. Projection and orthogonal projection. And it's just a nice exercise to see the definitions. If I have an orthogonal projection, then the corresponding determinantal point process satisfies the perfect screening. Now, if we look at the second correlation function, k, x, x, k, y, y, k, x, y, k, y, x, and there is no this term. Here I need truncated second correlation function. It means I have no diagonal. This is the product of the first ones. And what I get is minus this product. Now, because of orthogonality, I can write it in the following way. I just have my kxy absolute value squared. Let me write it here. Determinant process plus perfect screening, and I get that the variance P of SF is just the integral f of x minus f of y squared times kx y squared dx dy. Sasha, do you agree?
Yes, yes.
Okay. Now, yes, thank you, Yanshi. And no minus here. Now, if I have a Pfaffian kernel, and usually it will be denoted like this and like this, let me just very briefly remind you that let me have a matrix A skew symmetric, and by n, do you see here? Yeah. Then I can conjugate it to the form, say, B here minus B transposed here. And if I'm interested in the determinant, I consider the block matrix, it will be just the square of the determinant of B. It means that in this particular case, it's natural to have some name for this determinant of B. I will call it Pfaffian of A, more or less by definition. To be more exact, we see that the square of my Pfaffian is determinant of A. If I say that Pfaffian will be a polynomial in entries of A, then I have the definition up to the sign, and all what I need is to say that, for example, Pfaffian of J is equal to 1, where J is a standard skew symmetric matrix 0, 1, minus 1, 0. It was the definition. I will not use it, because all we need is the truncated second correlation function. Now my Pfaffian kernel will be 2 by 2 matrix kernel. I will say that my correlation functions should be defined by Pfaffian of the following matrix. So these are blocks 2 by 2. I get matrix 2n times 2n, but I need it to be skew symmetric. That is, my kernel should satisfy that kxy transposed is equal to minus kyx. This is the definition of the Pfaffian kernel, and I don't want to state you the exact proposition because it's a bit more complicated in this case. If I have a projector plus some additional condition, then I also have perfect screening. So this term vanishes. I need to tell you what is the corresponding truncated second correlation function, and I will just write you the answer. If I have a Pfaffian point process, and my perfect screening, then my variance is once again 1/2. And here I get just the determinant of my kernel. In a sense that it is a 2x2 matrix. I have a determinant of 2x2 matrix that is just the product of the diagonal entries minus the product of two other entries. If there are questions to this part, then it's time to, yes?
What do you mean by K2 equal K for the
I mean that I have a matrix 2x2. Just let me show it on the second blackboard. You ask about this condition.
No, on the left. Yes, correct.
It just means that I have an operator in the space L, say 2 of R times L2 of R. And it is a projector. It is not an orthogonal projector, just a projector. Well, it's if it comes from the orthogonal ensemble, it's skew orthogonal in a way. I can write something, but it doesn't help here. Now we have two formulas for the determinantal case and for some of the Pfaffian cases. I want to very briefly remind you the nicest possible example in the determinantal case, that is signed kernel that we've seen several times. And then I will show you what we have if we pass from determinantal case to the Pfaffian ones.
Why in the argument of sign?
Say it again.
Why in that? It's a question. Sorry.
It's okay. So, let me remind you that what I actually need, I need to construct a sequence of functions f such that the variance vanishes. And as Sasha proposed in his paper on determinantal processes, I consider phi of r t of x, which is 1 for x less or equal to r, which is 0 for x sufficiently large, and which decreases logarithmically. Let me try to write it correctly. Log of x minus r plus 1 over log t minus r plus 1. It seems that everything should be okay. What I want is I have 1 here, r minus r here, and some t that will go to infinity. A picture like this. Now, the variance for sign of this particular phi of phi r t, you see that in fact we should estimate a lot of integrals because we will actually have a picture like this. Let me think just about x and y positive at the moment. Nevertheless, even here I have r and t, r and t. And if you look at the formula and you look at what I want to integrate, r t x minus phi r t y k 9 squared. You see that, okay, we have 0 here, we have 0 here, but then we have several places with different functions to integrate. But I have only one place when n square here, when this is the function of two variables. And it's the most interesting case. Let me show what we do here. Just the difference of the logarithms looks like I will estimate only this term. Looks like the logarithm of the ratio. So actually this part will be less or equal to some constant depending on r over log square of t. And here I have just the integral of the logarithm squared of x over y. And I have the x minus y squared here, dx dy. Now think about it for a moment. You will see that it is less or equal some constant over logarithm of t, and it tends to 0. More generally, if we're interested in the determinantal case, we have such a proposition. We're interested in the so-called integrable case, so I will consider a kernel of the form ax by minus a y b x over x minus y. So if I look at k x y modulus squared, it will be some nice function over x minus 1 x minus y squared. And part of such a proposition is if c of xy is sufficiently nice in the following sense, that is less or equal x over y to the power alpha plus y over x to the power alpha, where alpha is in 0, 1, then this integral will tend to 0, and I have some more simple, this is in fact the estimate for this part, and I have more simple estimate so that these integrals will also tend to 0. Actually, what we see from here, in the integrable determinant case, we have the square of my kernel, we have x minus y squared in the denominator, and thus we can think about the absolute convergence here. And the first difference, one of the two main differences, will be that in the Pfaffian case, there will be no absolute convergence. Let me pass from the most simple. Yes?
Right now we proved that for determinantal process is rigid. It's is rigid. Under assumption.
If we have an estimate for the kernel, then the corresponding process is rigid. Now I pass to the Pfaffian case.
What process?
And once again, I want to show you the main features on the most simple case. Here I should be a bit more careful how Andrei told us. If I start from GUE, pass to the corresponding eigenvalues, then take some point in a bulk, expand it in a proper way, sine kernel. And in fact, now it's known that there is a long list of ensembles for which I have sine kernel if I consider the corresponding bulk scaling. Now, if I'm thinking about GOE or GSE, I can do the same, and what I actually get will be two very similar but different processes. One of them, both will be Pfaffian. One of them will be K sine for GOE. We usually write beta equal 1, coming from the log gas theory, and from GSE, it will be beta equals 4. Here the formulas are slightly more simple for me. I will consider only this case. So K sine 4 xy will be of this form: 1/2 K sine xy here, K sine, well, let me write yx. Here for sine it doesn't matter, but in general it should be like this. Here I have the derivative. Here I have the integral. Here we are. First of all, you can believe me that in this case I also have the corresponding property. This 2×2 matrix kernel is a projector. In fact, what we actually need, we need to consider the second truncated correlation function, that is the determinant. We should integrate it. And what we get here is the square of the sine kernel, which is already a projector. Here we have the product of the derivative times the integral. And there will be no problem if we use the integration by parts. Everything works. This is okay, and more or less because of that, we get the perfect screening here, and we're interested only in the formula on the right blackboard. Let us look once again at the term of the form and times my phi r t x minus phi r t y squared. What do I see here? Let me write it explicitly. Here I can just rewrite it as the integral from 0 to y minus x. And here I have, in fact, dependence. I will have only dependence on t, so it will be the integral from 0 to infinity sine t, well, some constant over t dt minus the integral from y minus x to infinity and here let me also write it explicitly. I should differentiate my sign. What I actually get is the cosine of x minus y over x minus y and minus sine x minus y over x minus y squared. And I also have this term. This is just the determinantal case. And what I know that if I have the estimate like this, then it will be similar to the determinantal case. So for this part, this is nice in that sense. Here I have also the square in denominator. Here the integral converges, it will be just some constant, and it's easy to see that this integral is just okay. It is bounded by some constant over x minus y. Now, if we expand everything, we see that the only term which is not of that form is my cosine times the constant. I can rewrite everything in the brackets, just sum c of xy over x minus y squared, where in fact cx y will be just bounded, and I add some constant times I know that there will be no problem with this term. How many minutes do I have?
15 minutes.
Perfect. And let me think about this one. Looking at the integral here, it's natural to set lambda equal x over y. And what I actually get is that the corresponding integral will be less or equal I get the square of the logarithm once again in the numerator. I will have 1 minus lambda only one time here, multiplied by cosine of x 1 minus lambda. It's just x minus y dx d lambda. Now, if I think about the absolute convergence, there is no absolute convergence. So I should do some more work. For sine, everything is simple. I just integrate my cosine with respect to x. What I actually get is the, okay, less or equal logarithm squared t here, and here I get just the integral from 0 to infinity logarithm squared lambda. Integrating my cosine, I get 1 minus lambda in the denominator. Now it is bounded and everything is okay. But you see that if I have some kernel that comes from the orthogonal ensembles, I will think of these ones. That what I actually get, forget about sign here, I will get a kernel of this form. It means that when I expand everything, most of the terms will be of a form like this, at least with x minus 1 in denominator. It means that all that we can do at the moment is just estimate them in a way term by term. We extract the constant part, then we extract the oscillating part, and then the rest converges absolutely. So this is some amount of technical work. But this is only one of two obstacles that I actually have in the Pfaffian case. Now let me write the formula for the variance once again. And we have the second term on that blackboard. Till the last month, we were sure that if we are at least in the case when beta equals 1 or beta equals 4, then we do have perfect screening. But then when we try to write explicitly, I can state now just a proposition, for example, for Pfaffian decimal process. Doesn't hold. And it should be explained why, because it's quite a natural ensemble and, well, no external field in any sense. There should be some explanation. Of course, there is an explanation in a mathematical sense. If I will have a couple of minutes, I will explain you why this doesn't hold for Bessel. Now I want to tell you, well, what should we do? If you think about this integral, let me put phi r t here, and let me write once again the picture. And I will denote it for a moment by d of x. When I take r sufficiently large, well, my square of phi looks like 1. More and more looks like 1. So if I'm interested in my variance tending to 0, and I know that the second part does tend to 0, what I want to say that just the integral of my dx also should be 0. And it's true. It's a real proposition. Pfaffian Bessel process here. What I do have is the corresponding property. So the expression inside the brackets is not 0. But if I average it over all r, then I actually get 0. And to be more explicit, how we should why this will be more or less enough for us. I just subtract these two expressions. I get the integral over r of phi of x squared minus y times d of x dx. And here I get my standard situation. I can look carefully at this kernel. I have some oscillating term, and I can see that actually when my t tends to infinity, I will eventually get 0, phi of r and t. And the situation here is much more simple than for the second term, because well, it's one-dimensional. So no, I have some more parts, just the question is 1 more minute. Well, let's stop here.
Any questions?
So what about Pfaffian array? So what is the situation with Pfaffian array process?
At the moment, I believe that everything should be the same as for Pfaffian Bessel. But if we remember our beliefs...
No, but the particles, the two half lines are very asymmetric.
Yes, but nevertheless, at first glance, this should happen.
Any more questions? Let's thank our speaker again. And we reconvene at 10:30.
But don't look.
Our second speaker today is Jordan Emme, and the title is on the board.
Thank you very much. So I'm very glad to be able to speak here, especially since the weather is even better. I know we all have had a rough night, including me, so everything I will say will be elementary. So I will present a joint work with Pascal Hubert on some sort of random matrix products that arise from arithmetic considerations. But before I delve into that, I would like to do a first elementary remark in order to motivate the intuition for what's to follow. So the first part is just an elementary remark. So, yeah, the remark is the following. So let's say proposition. If you take a sequence of matrices, of square matrices, and you assume that they converge in the sense of C0 mean to a matrix A. So that's the first condition, and such that the sequence of the means of the norms of these matrices is bounded by a quantity alpha, then the following product converges towards the exponential of the mean. So, in the case where the matrices are of dimension 1, this is a triviality. And when it's not, it's close to B, but I will make a proof, and that will be the only one I'll make, I think. So, for the proof, okay, so you could maybe try to do sophisticated things for that, but we wanted to have an elementary proof to give some intuitions for what's to follow. So, what can you do that's elementary? Well, you expand this product and you compute. So, if you take the product and you expand it, you end up having this sum. Can everyone read okay? All the so you end up having this sum, and you will just, since you have a series, you just apply a bounded convergence theorem. So you need to bound it. So we bound the main term. So how do? You look at that. So for any k in k, and for all n in n, so you just take your product, you apply triangular inequality, and then you, okay, I didn't precise which norm, but you take a submultiplicative norm. And so all this, you can say that it's smaller than 1 over factorial k times the mean, n minus 1 to the power k. And so this is smaller than alpha k over k factorial, and this converges. So that's not that's not deep. But then you want to compute the limit for every k when n goes to infinity of the main term. So what you prove next. So we prove by induction on k that the limit of this mean, when I sum over all the ordered k apples, so I will prove that this is 1 over factorial k times ak, and then this will infer that the limit is the exponential. I said, so the initialization is just the first condition in the proposition. And how do you do the induction step? Well, it's easy. You consider one over n k plus 1 so the last index I will not denote it ak plus 1 but L, just to make my life simpler. And what I do is that I just start my summation over L in order to have this limit, to be able to make this limit appear. So I start my summation from L, and I sum here on the k poles smaller than L. Times AL, and this behaves like L bar k times AK over factorial k. Okay, so there is a rest, I don't want to consider it, but if I plug this in, what I end up having is, so this will be equal to 1 over n times 1 over factorial k times AK times this sum, k or n minus 1, L over n to the power k times AL. And here I will just use a classical lemma. So lemma. That is, if I take a sequence un of complex numbers, say, such that, the mean of this sequence converges. And if I take a continuous function on R or on C, for what I'm doing, R is enough, then the following quantity converges. Times UL goes to U times the mean, the integral of G on 0, 1, when n goes to infinity. And so for this, you just do an Abel transform, and that's why you need the hypothesis on C1, because you need to bound some terms on G. It's nothing. But it explains, if you just internalize this lemma, your function G is just taking the case power, and so by integrating you get your 1 over k plus 1, your A, and everything is good. So okay, this is, there is a priori nothing deep about it. Very, I mean, a priori, but I want to now to introduce the main object of the talk and explain to you by the end why this is interesting and why it gives some intuition as to what I am going to do. So, okay. So I will just introduce now the main object of the study. So it follows from some works, some classical work in arithmetics of Bessino. So following the works of Bessino in the 70s. We are interested in the following quantity. So let n be an integer that I can write with its binary extension, and I belongs in 0, 1, and define S2, which is equal 0 k minus 1, which is just the number of ones in the binary extension of n. I am interested in this quantity, and especially in the following sets. So we are interested in the following sets. So I define for any integer n, a, and for any integer d, so positive, non-negative integer a and just integer d, I define the set EAD to be the set of integers that satisfies this equation. And so this comes, I mean, the motivation behind is that this equation appears in arithmetic correlation functions of arithmetic functions. I don't want to give of arithmetic functions. So, okay, this if you look at the first papers from Vecino on statistic independence of sum of digit functions, this quantity appears and plays a central role. That's what motivated us to study it. I won't get into much detail, but Vecino proved, in particular, that n can be partitioned into arithmetic progressions such that the function which maps n to the difference in the number of ones in n plus a and n is constant on the elements of the partition. This is even better than that. What it says is that for all A and D, these sets can be seen as a finite union of arithmetic progressions.
Partition into finite domain.
N, no. Infinitely many. But if you take this set, it's finitely many arithmetic progression. And then you have to take D on all of Z, a priori. Okay? But since here it's finite, the asymptotic densities exist. I want to give an idea of why this is true, why these are arithmetic progressions. And in order to get the idea, you only need to consider what is non-trivial in this, and what is non-trivial is how the carries are propagated. So we will check for a equal 1, see how a carry is propagated, and then I will explain when you get something different, when you take something different than 1, how to see what happens. Okay. So example. If you take a equal 1. If you take a equal 1 and you take d greater than 1, all these sets will be empty. Because what can you do? When you add a to n, you can only gain the ones that are already in A or propagate carry, and so you lose ones. So you cannot get more than there is already in A. So if d is greater than 1, this set is empty. So E1. E11, well, you just need to take an even integer. You want to put a 0 in place where there is a 1, so you take an even integer, you get your 1. If you want E10, you don't want to get this one, so you need to propagate a carry, but you need to stop it right away, otherwise you lose too many ones. So if you actually do it, you can see that it's 4n plus 1. This one will make it odd, but the 4 ensures you that there is a 0 after in the binary decomposition, and the carry stops right away. So you just flip the 1, 0, 0, 1. And you can carry on, and what you would get, so E1d would be 2 to the power 2 minus d n plus 2 minus d minus 1 plus 1. Minus 1, sorry. Okay, this is just saying if I want to lose many ones, I put a sequence of 1 and then a 0 to stop where I want in the binary decomposition.
For negative d.
And this is, yes, for d. Exactly, thank you. Okay. So now, okay, you have for 1, that's not much. You need to know how to compute them for every a. Well, property. So for every a in n and d in z, So what is 2AD? It's just the set 2n plus b, a being in EAD, and b being in 0, 1. I will explain this case quickly, and I will not explain the following recurrence property. So, how do you do that? If you're at primary school and you want to compute a sum, you put one number above the other, and you compute like that. So we're going to do this. 2a, let's say it's binary, I haven't given a notation, I underline it, it means it's binary decomposition. It's a followed by a 0. 2n plus b is binary decomposition, is n followed by b. When I sum the two, I get my b here. So it will not intervene in the difference because it will not, it will be killed, it's the same here. And what arrives here is n plus a. So that's why you go back here to n being in EAD and everything is good. So if you believe that, you believe the following one. If I take an odd integer, then this will be the union of these two. Oops, forget half the things. Okay? It's the same sort of thing. You can put either, except here now there is a 1, and so depending on the b, you either propagate a carry or not, and you need to take this into account for the differences that come after. You need to compensate for it. Okay, so now you see we have our E1. We see how they split or not, depending if you get something even or odd, and you have your arithmetic progressions. And so you can define finally the main object, which is this one. All right, you just take the asymptotic density of these sets, and the remark is that mu a is a measure, is a probability measure on Z. Because if I fix A, and then the EADs, when D goes over all the integers, makes a partition of n. So I'm just saying that it's a sequence of positive numbers whose sum is 1. And so now, if I because all the sets are finite union of arithmetic progressions. No, yeah, sure, no problem. And also you can see that the arithmetic progression will always have. The reason is always the power of 2. Okay. So your actually your mu a is even better. You know, these will be dyadic numbers. But anyway, that's not important. Okay. So we have induction relation on the sets. We can infer induction relation on the measures. So from the relations on the sets EAD, we get almost where I could have started with if I didn't want to give any motivation, but we get the following. Mu 2a is equal to mu a, and mu 2a plus 1d is 1/2 of mu a d minus 1 plus mu a plus 1 d plus 1. Okay, that's standard. So, okay, this could remind lots of stuff. This could remind two automatic sequences, so Stern sequence, or as Sébastien talked about, the dual operator of the doubling. But here we don't have numbers, we have measures, and we have a shift in the measures. And this will be very important. So now the question is, the question that we asked ourselves, is how does mu an behave asymptotically for a good sequence an. All right, so I will stop there for 1 second. Okay, so obviously you don't want to take the powers of 2. And actually you don't want to take sequences such that at some point you only multiply by 2 and get, so that means in the binary decomposition of A, at some point just getting zeros and having nothing happen. It's not that much more interesting to have only ones at the end of the binary decomposition. What you need to have is that something happens, in order for something to happen, is that there are zeros and one always, that there are always different blocks, that this is not bounded, and that at some point you never get just zeros or just ones after a while. So you always need zeros and one expanding. So we had first work with Sacha Prihodko, where we computed some properties of the mu a's depending on the quantity, the number of blocks of ones, and that got us thinking to the question of, if I take my sequence in a good manner, because in a random manner, but because I am a dynamician, this will be given by the prefixes of a symbolic system according to some ergodic or measure on it. Then what happens? How does this distribute? Well, so I will spoil. So the third part will be central limit theorem. Are there any questions so far? Okay, good. So central limit theorem, so just some notation. I will associate to any element of the unilateral full shift, I will associate, so for define a sequence, an integer sequence, which I will denote AXN, and which satisfies for n, AXN is the sum of xi 2 to the power I and of length n. So I take the prefix of length n and up to the up to the symmetry, which doesn't actually matter. You think of this as the binary decomposition of A. All right. And so now the theorem is the following. So it's with Pascal. So you take nu to be a shift invariant probability measure. So on 0, 1, n, and you take it different from the Dirac mass on the periodic point 0. And you also don't want the Dirac mass on the periodic sequence of ones. Then you know that there exists a positive quantity, which is just the asymptotic variance, and I will go to that in a bit, such that if I renormalize my measures in a proper manner, which is the following, so such that let mu, so sorry, for all elements in the subshift, I can define the renormalized probability measure in this way, which will be square root of v nu n times z. And then for nu almost every x, I have weak convergence towards the centered normal law. So n goes to infinity, and it's weak. So that's the theorem. So basically what it tells you, in other words, is if I take any generic sequence for an ergodic measure, and I follow it, and I have a sequence of integers that are given by the prefixes, then up to renormalization by the good quantity, I just have my normal law. And I don't need independence.
But Jordan, there seems to be an implicit assumption of the variance in which maybe is not related.
What is...
The variance has to grow linearly.
Oh, but this is... Yeah. But I will tell you. You just need to compute... What I mean is we're able to compute the asymptotic variance, which grows linearly in a sense, because the variance over n, the variance of mu... I will write it, okay? Yeah.
Sorry,
oui.
you said ergodic, but you didn't write it.
Oh, yes, it's shift invariant, shift invariant, ergodic. Thank you, yes. I'll give just the main ingredients of the proofs. You will see where it appears. Okay. So, the main ingredients of the proof. So, the ID, it's not an ID, the method we follow is Markov's moment method. We compute all the moments. So from Markov, we compute all the moments and we show that they converge towards the moments of the Gaussian. So how do we do that? Well, I erased it, but so I will rewrite it. You had mu2a, which was mu a, and mu2a plus 1 d, which was this. The moments of the functions are given by the characteristic. The moments of the measure, sorry, they are given by the characteristic function. If I compute the characteristic function, from these recurrence relations, I get some relations, also recurrence, on the characteristic function. So from this, you infer that for all theta, you have the characteristic function of mu2a, which is equal to the characteristic function of mu a. There is nothing. But here you have a shift. So this implies just multiplying by a character in the dual. And so this is okay. So if you just compute, And now you see where the matrix will arise from. If I want to get the mu A, I look at the decomposition at the binary decomposition of A, and this will give me a matrix product. So I take two matrices, which are the following ones. And I have the following. So if A is equal to the sum of the AI to I goes from 0 to n minus 1, then the characteristic function of mu A is given by the product of these matrices, where the choice of A0 or A1 is given by the AI. And you apply it on the first two that you're able to compute. And this is fundamental. That's the only thing, really, that you use and that you're able to use. Okay? If you understand this product of matrix, you understand everything for this problem. So now I will answer your question, Sasha. What do you need to do in order to have a central limit theorem? The first step, you compute the mean, and then you compute the variance. Okay, so the mean, you could compute it in a very easy way. What I'm going to say is quite convoluted, but it's in order to explain what happens next. So you want the derivative in 0 of the characteristic functions. You just make a Taylor expansion of these matrices, and you multiply them together and see what happens. So we take the Taylor expansion of the matrices. Sorry. So A0, so it will be the matrix okay. And you can do the same thing for A1. I will call this one I0, this one alpha 0, this one beta 0. I do the same thing for the A1. Now, what you can notice is that if you take these values in 0, since these are probability measures, it's 1. Okay? So for the first moment, you will have to understand. So, say the Taylor expansion, if I don't take into account the second moment, it will be 1, 0, and I0 plus I theta alpha, A0, I an minus 1 plus I theta alpha an minus 1. And I apply it to the vector 1, 1. And I want to look at the term, the theta term. So how do you get a term in theta? You choose 1 alpha, you multiply all the others, you choose I. And so what happens is there is a miracle. I of 1, 1 is 1, 1. This is normal. We have stochastic matrices because we want to keep probability measures. But also, 1, 1 is in the kernel of the alphas. So there is no mean. Okay, the mean is 0. Why did I want to compute it that way? Because now, if you want to compute the variance, how can you get a term of quadratic order? it's either two linear terms or one quadratic term. But you don't need to check two linear terms, because for the same reason, they will be killed. So in order to compute the variance, you only need to consider the quadratic terms. How much time do I have left? Is there
20 minutes.
20 minutes? 10? Okay, 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 no, good. All right. So you only need the quadratic terms. So, let's say, so the variance of mu a is just given by 1, 0, sum of the a0, I minus 1, beta ai, 0 to n minus 1, in 1, 1, applied to 1, 1, plus something else that comes from this guy, but I don't need it, it will converge. So plus something, plus a constant here. So I just need to understand this. But computing the IAI is a bit involved if you don't see what's next. Well, since 1, 1 is an eigenvector for both I0 and I1, then you can trigonalize them simultaneously. This seems to be sort of a miracle from the 2 by 2 case, because yes, of course, they have one eigenvector. But actually, it comes from the way the carry propagates. If you were to write the matrices for a higher for basis of greater order, you would have bigger matrices, but you would still have an invariant flag, because the carries don't propagate that much. If you write it, you really need just to write it, and you see your flag on the matrix. There are lots of zeros everywhere. So this is actually not that much of a miracle from the 2 by 2 case. It always happens. So we trigonalize I0 and I1 simultaneously. And it gives you this. 1/2 and all right. And so you see, when you will multiply this, you will have correlations that appear. If you do it properly, you see that the variance will be something like n over 2 minus 1/2 of the sum over the correct things. So n minus 2, sum for k equal 0 to n minus I minus 1, bk, whoops, oh, I didn't, okay, bk plus I over 2i, where bk is minus 1 to the power ak plus 1. I just changed this, the 0 in the, sorry? Oh, yes.
Variance of mu
I'm just saying for any a, I'm not even yet, the variance, we know how to compute it for any integer a, and I just assume that a is an minus 1 a0, because okay, we effectively only use it on the along prefixes, but we can compute the variance for any integer, and it's this plus some rest that not important, something smaller than n. So then, if you have an that is given by prefixes of generic points of ergodic measure, you're able to compute the asymptotics of this over n, and this will be your v nu. And it's non-zero exactly when the ergodic probability measures are not the Dirac's at 0 and 1. So you can always renormalize. The next step I will not explain, but because the computations are much too involved and it doesn't bring any light. But there are still some elements in it that bring some light. So the first one is, so you remember I told you, okay, my matrix alpha for the linear terms are in the kernel of 1, 1. So I don't consider them for the variance. Yes, but what about higher order moments now? Because I could very much imagine moments of order 3. I take 1 alpha, 1 beta. And if, so I can have something with many my alpha, and my I still, and then a beta, and then my 1, 1 goes, it hits the beta, it's not killed. There is yet another miracle. It's the following, is that the alpha i's are left eigenmatrices of the i's of eigenvalue 1/2. And so you're able to see, if you compute it, that really the alphas don't matter because they span geometric sums, and you're able to check that it will not matter. Why will it not matter? Now it's the final remark, is that if I look at my renormalized, so I go back at the, take an x, I renormalize it. If you look at what it is in theta, it is mu axn, and that's what's crucial here to understand. You have this equality. Okay? So you have some powers of n that appear and that will kill many, many terms, and you need to understand, well, how the terms will be small o's of some power of n, and you want it to be small so that it's killed in the renormalization process. Okay, you study that, and what you actually happen to see is that the only terms that actually appear are the quadratic terms. Nothing after, because otherwise you would have too few terms, because before the alpha, there is this 1/2 that will kill everything. You need to do properly the computation. It's not obvious, but this is the case. And so morally, you want to understand ix0 plus minus, sorry, theta square over 2 v mu n, no, not over 2, sorry, beta x0 I x n minus 1 minus theta 2 over v nu n beta x n minus 1. There is a, you want to consider this because actually they are the only terms that will appear in the computation of the moment. Okay, so you see I'm being a bit dishonest because the writing suggests that it is essentially the same case as before, but it's not, because the i's here are not the identity, and it makes things much, much more complicated. But still, the idea is the same, in that at theta equals 0, you have some cocycle, and you know how to compute it, and for the identity, it's of course trivial. Here, we have this correlation, it's what we did in this case, we know how to do it, everything's fine. But there is this small perturbation that makes non-trivial thing appear. So I know I will soon have to stop. So what I'm going to say now, okay, maybe I said arithmetic application, and I just give one theorem that is of arithmetic nature. Maybe I could give a bit of motivation more. So there is a conjecture by Cusick, which is that if you take any integer, the sum for d in n, so non-negative integers, the 0 is in it, I insist, this is greater than 1/2. We don't know how to do that. Morally, if you take a random integer like in the sense of the asymptotic density, and you add it to A, well, you have more chances of gaining ones than losing them. We don't know how to do that. And the second is that this bound is optimal, which is fairly believable, but of this sum. Well, we proved, I mean, one of the consequences of the central limit theorem is that 1/2 is an accumulation point for many sequences of A.
The second line is conjecture or result?
Yeah, these two are
Conjectural.
This is conjectural. I mean, because we just proved that it's an accumulation point. So then having this one would imply the other. But it's fine. So that's one of the things you can do if you're interested in arithmetics. And the other thing, like for what comes next for me now, would be to understand this idea of perturbation of the cocycle, not to have an ad hoc method for this sort of matrices, but to know precisely which properties on the matrix that we had, which ones are the ones that are really necessary for it to have this sort of property to arise, which is morally having the exponential appear after a small perturbation. Okay, so I think I will stop here. Thank you very much. Thank you.
Are there any questions?
So in this Gaussian conjecture, if you replace strictly inequality by not strictly inequality, is that true?
If I replace
Strictly inequality.
by inequality, no, we can't find anything that is 1/2.
Okay.
Okay, the conjecture is really that. What I was insisting on maybe is that it needs to be greater than non-negative, because if you take positive integers, then it's false. We have counterexamples. The thing that happens at 0 is important.
So there is a famous theorem by van der Waerden about arithmetic projections.
Yeah.
So if you partition the integers into 2 or finite number of subsets, then one of them is rich, in the sense that it has finite arithmetic progression of arbitrary length. Then there is a generalization, which is the Erdős-Turan conjecture, which was proved by Semeredi and independently by Furstenberg. When you replace the finite partition and you take a subset which has positive upper density. Okay. So the question is, do you think that some of your ideas could be used to maybe get an alternative proof of this result, or at least a weaker version of? I don't know. The concepts are common, but maybe they are unrelated. I don't know.
Honestly, I don't know. I would hope so.
Yeah, me too.
In the current state, I would say no. From the thing. But maybe understanding better this sort of limit laws and having more richness than just this sort of example, maybe this will give rise to understanding better the sort of arithmetic progressions, because as I said, we don't know what. We have some ideas of what's really necessary, and there are some things that just simplified our computations. But if you take these sort of measures which arise from asymptotic densities, you will have this sort of shift that appears, and so exponential. I mean, the characters, and so you will always have sort of an analytic perturbation of your cocycle, and maybe you can hope in some case to do this sort of things. I don't know. I need to do this. Thank you.
Any more questions?
If you do the same in base 3 or 5, or does everything go through?
I think, but I wouldn't be able to write it like to write something for any base. Like if you give me base 3 and work on it, I will do it. But It will just be the same, more or less, computation. Like the only concrete difference, I think, in base 3 is that the mean is non-zero. So you just need to shift it. And then there is still an invariant flag. You can still trigonalize in the same way. But it will be the same sort of computation, so you just need to do them all over again. I don't think there is anything new arising from it. There is one thing, though, that is, I think it's interesting. So if you take really there are two ways to generalize this in base 3. You could think, I take the sum of digit functions, that seems obvious, I try to do it, and then you have non-zero mean, and then you have things that are complicated. Or you can take the function that counts the non-zero entries in the thing, which is not natural, but okay, I can see it like that, and then it's much more similar. There is zero mean; the things are very more closely related. That's okay.
Any more questions? Well, let's thank our speaker again. And we reconvene in 10 minutes, 35.